Okay, so this is the second class of the DMM, second part of the class, and that is going to conclude the multimeters session for this week. All right, so the second part of that, we're going to continue from where we left off, and we're going to look at the DMM symbols that are on the dial of the digital multimeter. Right. Also, as one more thing, I'm going to give you a link to a short video telling that I talk about how to read the analog version. And if you watch that, I think it's about 15-minute video, you should be able to have you should have no problem with reading the analog scales, right? And if you still have a problem, please, by all means, let me know by talking to me in person when we meet in person, or send me an email. Okay, so the common symbols on the digital multimeter. This little here sign with the V with a tilde one here stands for the AC voltage. As I said in the beginning of the previous class, is that the multimeter, the difference between multimeter is and a hammer, for example, is that the multimeter can do more than one thing, depending on how you set it up, what functions you choose how do you choose that thing to function. So if you turn the dial onto this little V with a tilde, you're going to turn that meter into a voltmeter that is capable of measuring AC voltage. And I think right now, because when I was talking to Ms. Abir, you're actually studying the AC theory right now. So that's, well, there you go. So the AC voltage can be measured if you switch the multimeter into this kind of a sign here. So then if you switch, depending on whether you have a switched range or auto range, in the switched range, in the auto range, you're just going to click either on this or on that, depending on what type of voltage you want to measure, and the range is going to be chosen automatically by the meter. If you have a switched range, then you're going to not only choose the area that has either the voltage, DC voltage or AC voltage, but you're also going to choose the range. By choosing the range, like for example, if you choose the range of 50 volts, then you're setting up the meter to measure up to 50 volts DC or 50 volts AC. Then over here is also, instead of volts, then a smaller version of the voltage would be millivolts. So some meters have that. Some meters don't, some meters do, depending on who made the meter, the model number, and whatnot. And millivolts are basically, the M stands for milli, which means times 10 to the negative 3. So if it's well, if it's 1 millivolt, it is 1,000th of a volt. Okay, so you can set up the range to up to maybe 20 millivolts, up to 200 millivolts, depending on the measurements you're dealing here with. Okay, then over here, the little sign of A stands for amperes, and amperes is the unit of current. So instead of having a voltmeter, you're having something that's called a current meter. All right, so then you're measuring current, and then amps or milliamps. This Greek omega sign stands for ohms, and ohm is well, unit of resistance. Now, just to make sure that we know what we're talking about, with this one here, you can measure only the devices that have passive resistance. So, in other subjects, you're going to have the theory as well that talk about, and during which you're going to study something that's called impedance. All right, you can't measure impedance with that setup here. You cannot. This is only going to measure the ohms, or the ohms is going to measure the resistance, and it is going to only measure the passive resistance. Like for example, a resistor, just a regular resistor that you're using in your breadboards for your labs and projects. Okay, Do we have that? Just hold on, guys, here for a sec here. All right, so I think we have the closed caption enabled or not here. Let me see here. Um, just bear with me here for a sec, guys. Captions, English, English. Okay. I think we should have the closed captions enabled with this here. If not, let me know, okay? Sometimes I'm fighting with the setup. All right, so the difference between the resistance and impedance is that, for example, hold on, guys. Captions, English, yes, we should have that. Okay, so the difference between the resistance and impedance is the passive resistance does not depend on the frequency that we apply. Right? So, for example, the resistor, if the resistor is 100 ohms, it is going to be 100 ohms no matter what. And what do I mean by no matter what? I mean that if you apply a DC voltage to that resistor, you're going to have a resistance by the device, which is the opposition to the current flow, and the value is going to be 100 ohms. If you apply AC, and if you change the frequency, if you lower the frequency or you make the frequency higher, that resistor is going to resist with the value of 100 ohms. And that is not going to change. If you have a coil or inductor or a capacitor, then things might change a little bit. So for example, a capacitor, the higher frequency you pass through the capacitor, the less the capacitor is going to resist. So if you have 100 hertz passing through a capacitor, it's going to give you a certain resistance. But if you have 500 hertz passing through a capacitor, then the capacitor is going to resist less. Capacitors love higher frequency, and they will conduct more if the frequency is higher. Coils or inductors are the opposite. If you apply low frequency through a coil, it is going to conduct more. If you raise the frequency passing through the coil, then the coil is going to resist more. So capacitors and coils act differently. So you can say that the resistors have a passive resistance, and and the reactive components, such as capacitor or a inductor, they have what's called a reactive resistance. The resistance depends on the frequency that is applied to that device. So the reactive resistance is called reactance. And with the capacitors, you get capacitive reactance. And with the inductors or coils, you get something that's called inductive reactance. Right? Now, when you combine, because the objects are made out of physical matter, so all components, all parts will have certain type of resistance, and they will have certain type of capacitive reactance or inductive reactance. Now, with resistors, the dominant quantity would be resistance. With the capacitors, the dominant quantity would be the capacitive reactance, and with the coils, the dominant quantity would be the inductive capacitance. But if you combine all those in one device, so if you combine it is its resistance. And if you combine its reactance, in combination, it is going to be called impedance. And it is also designated, it's also expressed in same unit, which is ohms with the omega sign, Greek omega letter, or you can write ohms as well. Right? So with the meter, with the regular digital multimeter or analog meter, if you switch it to this one here, you can only measure its resistance, the component's resistance. You cannot measure impedance. In order to measure impedance, you have to use different procedure involving different type of equipment. You can use the multimeter, but it's going to be applied in a different way. Right? This one here, this little sign here, that's a symbol of a diode, and it's a diode tester. In order to check the diodes, a diode conducts one way and it doesn't conduct the other way. So here is the positive side. Here's the positive side of the diode, and here's the negative side of the diode. And if you do something like a forward biasing, which means you apply the positive terminal into the positive side of the diode, and the negative potential to the negative side of the diode is going to conduct. If you reverse the polarity, the diode is going to prevent conducting. By the way, this positive side of the diode is called anode, and the negative side of the diode is called cathode. Right? Now, how do you remember which is which? Because you can remember that for maybe 30 seconds, and then you're going to have to look up or Google things, which is anode, which is cathode, when it comes to diode. Well, the analogy I use just to remember things is, well, what's the best mark that you can receive? What's the best grade that you can receive? A plus is the biggest mark you can receive. A plus, that's what you want. So associate A with the plus. Anode, positive. Anode plus, A plus. That's the anode, positive. That's the cathode, which is the other one, which would be the negative part of that. If you put the positive lead of the meter, the red lead, into the positive side, or into the anode, and negative side in the cathode, you are going to get some sort of a number showing on the meter. And that means the diode is conducting. And if you put in reverse, you're just going to, well, for the most part, the display is not going to react. So that means that's the diode is reversed. Now, if you have something that's called like a zero or something like that, that means that the diode is short. Basically, it's shorted, it's damaged, right? Or if you put both sides and you get no reactions, then the diode is open. Right? So that's how we use the. So what is the number that you're getting on the diode? On the display when you forward bias it, and the diode works fine. The number you are going to see is something that's called a forward bias voltage. Right? Now, different diodes will have different forward bias voltage. Like for example, if it's a silicon diode, the voltage here, you're going to have something around 0.7 volt, because it takes 0.7 volt to start punching through the diode. The diode is not a piece of wire. The diode needs a little bit of a voltage to make it conduct. So with the silicon diode, you're going to read about 0.7 on the display, which is the forward bias voltage, which is the voltage that makes the diode conduct. Right? If it's something that's called a germanium diode instead of silicon, it's just made of germanium instead of silicon, then you're going to see something like 0.3 volts, because it takes 0.3 volts to make the diodes to kick in to this forward biasing, and so the diode conducts. So the meter is going to show you something like 0.3. Okay. Now, things get a little bit complicated when we are dealing with the LEDs, which is the light emitting diodes, because the different colors of the diodes are made out of different material. And because they are made of different material, they will have different forward bias voltages. And sometimes, well, quite often, actually, pretty much almost always, what you're going to get is the forward bias voltage that is going to show up on the meter's display is not going to coincide with the specifications that are listed for that type of diode, like green diode, or blue diode, or white diode, or red diode, or whatnot. That's because the meter, when you connect, when you switch the meter into the ohms as an ohm meter, or the diode tester, you are going to have a certain voltage appearing on the leads. You can experiment with that next time you're in the lab, but that's going to involve borrowing a meter from your friend, so you can do it in pairs. Switch one of the meters into the ohm meter and switch the other meter into the DC volt meter, and touch the black leads and the red leads. The meter that is set up as a voltmeter is going to read the voltage that the other meter is putting out when it is switched to the as an ohm meter, or diode tester, or continuity tester. Okay. So that's how the diodes work. So sometimes, well, quite often, or almost always, the voltage that is being provided on the leads when you're testing the diode might not be enough to accommodate the needs of certain type of diodes, like, for example, light emitting diodes. So you're going to have something that is, well, much smaller value than the value that is being specified in the as a forward bias voltage of the diode. If you really want to find out what this forward bias voltage is, then you need to connect a circuit. Connect the diode, the LED diode, in series with the current limiting resistor. So you could have something like 330 ohms and 5 volts, or maybe 6 volts or 9 volts. Connect the diode and make a closed loop, and then measure the voltage across the diode. And it should be something close to what the specifications are saying on the data sheets of the diode. Okay. Continuity tester. Continuity tester is, well, checks for continuity. So let's say you have a piece of wire that is jacketed, and you just want to make sure that there is no break in that wire because you can't see through the jacketing. Okay, so you're going to switch the meter into the continuity tester like this here, and it is going to give you a little tiny beep, right? Well, it's kind of puncturing through. So first, touch those leads and make sure you get that beep, the sound. That means your meter works. And then start testing for any kind of wires that you're not sure, or any kind of 2 points, just to make sure that there's a continuity going through, right? So that's a continuity tester. There's some of the meters will have capacitor meter, so you switch that onto the capacitance meter, and there would be terminals on the meter that you can connect the capacitor to, and um, you can it's going to tell you the value of the capacitor. Some of the meters, which I don't see it here, sometimes they will have the HFE meter if you want to measure the transistor's amplification factor. Okay, so this one is not listed. So, well, And some of the meters also have temperature meter. So these are the most basic ones here. These symbols are often found on multimeters and schematics. They're designed to symbolize components and reference values. I just had to write that here, okay? All right, next slide. Let's continue on here. Measuring voltage. All right. Ooh, yeah. Voltage. What is voltage? Is the electrical pressure or difference of potentials. You're going to have different definitions of that, but by now you should know what voltage is. Yeah? 1 volt is the difference of potentials needed to cause 1 amp of current to pass through a 1 ohm resistance. Another little bit kind of a visual as far as definition here. Voltage is divided into 2 sections, AC or DC. Alternating current, direct current. By now, we should know what the differences are between AC and DC. Alternating current, AC, found in the household voltage. We have 110 volts or 120 volts AC in our outlet, in our wall outlet in North America. In Europe and India and maybe China and some other parts of the world, you have 220 volts AC. Direct current found in battery, like for example, a car battery, you would have 12 volts DC. For most accurate reading, while selecting the range on a switched meter, the high-end value of the range must be 1 step higher than the measured voltage. So if you are measuring 12 volts, you're going to switch to 5 volts range on the meter? No. Are you going to switch to 10 volts range on the meter? No, that's not going to be enough to measure 12 volts. What would be the next one? The next one probably would be 20 volts. So that's what the range that's the range you would switch to in order to measure 12 volts DC, like a car battery, for example. Right? For the so that's what the probe tips must be in contact with only the measured test points and nothing else. Make sure that you don't touch the metal part of the probes with your fingers. If it's a small voltage, like 5 volts or whatnot, then nothing is going to happen to you. But you might not get an accurate reading because your body also has a certain type of resistance and you're putting that resistance in a circuit with it, right? But if it's a higher voltage, you can actually get hurt. So that's sometimes people use the one hand in your pocket technique in order to measure some voltages. So you hold the 2 probes in one hand, and the other hand, you put it in your pocket just to make sure you don't touch anything else. So if you get some sort of a break in the structure of the leads, you're going to get your hands kind of, well, you can get your hands damaged, but at least the current is not going to flow through your heart if you use both hands. So now I'm going to come back to the last part here, but first here. All right. So this might help you with other subjects as well. If you are assembling any kind of a circuit on a breadboard or on any kind of training board or whatnot, concentrate on the current pathways first, and then see what parallel devices are to be added. It's a very efficient way of doing things, and it's going to make life so much easier for you if you just go from point 1 to, if you just keep connecting the dots, you're going to get lost. So these 2 resistors, if you're going to construct circuit like that, you'll have a power supply. What's the current pathway? Well, it has to go from one part of the power supply, go through all the loads and come back, right? So you know how to close circuit. So over here, it's a simple series circuit. go to one resistor, from that one go to the other one, and then I'm going and come to the battery or to the power supply. And if you need to verify, you just follow the current pathway and make sure that the current pathway is what it's supposed to be. After you complete the current pathways, then you worry about the parallel devices and connection of the parallel devices. In this case would be a voltmeter. Okay. So in order to measure the value of the load, which is like if we want to measure the voltage across R2 here, we are going, oops, my mouse, sorry. We're going to install the leads onto across the terminals of the resistor number 2, which means this voltmeter is connected in parallel with the measured load. Right? Now, here comes a little bit of a, well, I hate the word caveat, but let's say that. What's happening here? Let's take a look at the current flow. Here comes, in this circuit here, the current only can flow through these two devices, and that's it. There is no any other alternative way of the current pathway. Right? Current leaves the battery, goes through the first load, goes nowhere else but through the load, and goes to another load, goes nowhere else but through it, and it goes nowhere else and comes back here. Well, what's the problem here? Let's analyze the situation. The current leaves the power supply, goes to the first load, goes through that load, and it goes nowhere else but this. No. Look at that, we have a node here. So the current is going to split. Some of the current is going to go through the resistor. Some of the current is going to go through the voltmeter, and they're going to meet here and continue on to the power supply. So we have a current splitter here. Wow. Well, which brings me to that last point of the previous page. Well, in this case here, what is the parallel resistance of this R1? You might say there's nothing else connected to it. Well, there is something across that. It is the air, right? The air also has certain resistance. The resistance of the air is extremely high. And it's high enough that the current that is going to flow through the air across the resistor and come back here is going to be so tiny, extremely small, that we can just ignore the value of it comparing to what flows here. Which means the circuit is not affected by the air. It behaves as if the air did not exist and the current only flows through that. What is the idea of taking a measurement of a live circuit? Well, the first and most idea is to not alter the behavior of the circuit, which means that the resistance of this voltmeter is going to have to be extremely, as much as possible high to be comparable with the resistance of the air, which is also high. So it's this circuit here should not be affected by tapping in with the measuring device, which means the internal resistance of the voltmeter is supposed to be as high as possible. You're going to have certain resistance which is smaller than air because you need tiny, itsy bitsy amount of current passing through that in order to trigger the measuring devices or equipment in order to give you a reading. So you take a little tiny bit of a sample of the current in order to to show the reading. But the resistance of the voltmeter should be extremely high enough so the current that flows through that is going to be so small that is going to be insignificant comparing to the whole circuit. So the resistance of the voltmeter should be high in order to not affect the circuit. And that is the last point of that previous slide right here. The internal resistance of a voltmeter is extremely high, so the measurement can be taken without affecting the circuit, ideally. All right. Typically in the neighborhood of 100 mega ohms, and mega stands for million. So about, 10 mega ohms or higher. That's why some of the meters are more expensive than others. And what is the internal resistance of a voltmeter? When you purchase a multimeter? Well, read the documentation that comes with the meter. Right? So that would be the measuring voltage. What else do we have here? Measuring voltage. Because the internal resistance of a voltmeter is high, we can connect the leads straight onto the load and get the reading. Can we do this thing as an amp with an amp meter? No, we can't, and I'll show you why. But before that, we're going to look at measuring the resistance. Right, measuring the resistance. Resistance with the designation of R is the opposition to the current flow, and the current is indicated with the letter I. Unit is ohm, or the Greek letter of omega. Well, we all know all that. The quantity opposite to the resistance is called conductance, and it is designated with the letter G. So G, conductance, is the opposite of resistance, and the conductance is designated with the unit of S, which is Siemens. That's just a bit of a background information here. If a current of 1 amp passes through a component across which a voltage 1 volt exists, then the conductance of that component is considered 1 Siemens. Another little bit more background information. Well, I would ignore that. Yeah. Okay. Procedure. In order to make a resistance measurement of a component, first of all, we need to disconnect the power source from whatever the device is that contains that component. Then we need to remove the component or part of the component or part from the system before testing. And I here said common procedure would be something that's called lifting one leg. It's often enough to do that. And I'll explain that to you. Measuring using the lowest value if the over limit is displayed, and then next high resistance range. So if it's an outer range, it's going to find itself within the environment. If it's a switched range, you're going to have to find the range for the value. Okay. Why do we need to turn on? Why do we need to remove the component? Let me just bring up this. That's from the previous class. Let me just create a new file here. Create. Okay. Here's our pan. Let's get some nice blue color. All right. Let's say we have a circuit consisting of different resistors. All right. And over here we have a power supply. Let's say plus, minus. All right, follow me so far? Here's R1, here's R2, here's R3. Let's say we want to measure the value of R3. Well, first, we're going to have to make sure that the power is disconnected. Okay. And then we have to remove the component from the circuit. First of all, why do we need to disconnect the power in order to remove the device from the circuit? Sometimes removing a device, whatever it is, this is just a simple circuit here, right? But sometimes you get more complicated circuitry. And if you remove a component from the whole circuit and you still have the power on, the absence of this component could make the circuit behave completely different. And sometimes it can actually damage other components because it's not there. Okay? So we need to disconnect the power and we need to remove the component from the circuit. Why do we need to remove the component from the circuit? Let's say we have an ohm meter and we're going to connect the leads across that resistor in order to measure the value of this resistor. Are we really getting the value of this resistor? Or are we getting the value of something else as well? Well, look at this. This resistor here is connected in parallel with this resistor. So even if the power is disconnected, you stick the leads, you measure the total resistance of R2 and R3. Well, you're not getting the value of R3, are you? So what we need to do is we need to remove this. We need to remove that component from the circuit. And then when you connect the leads across that resistor, you are going to measure that resistor only. But I said something about lifting one leg. Let's get the connections back. Lifting one leg means just disconnecting one side of the component. Where's my eraser? Here it is. So if you just disconnect one leg of that resistor, you have electrically removed this resistor from the whole circuit for the purpose of measurement. So remember, the ohm meter introduces tiny bit of voltage to pass through that component in order to create a current flow, and its internal circuitry is going to measure the current, and based on that, it's going to calculate the resistance of whatever is connected. So the current flow will go from here to here. That's it. That's why we also need to not only we need to remove we also need to remove the power from that, because if we have the power applied and if we have the component as not removed from the circuit, you're going to apply voltage to some voltage that already exists there. Not only are you going to get a false reading, you can actually damage either circuit or the meter or both. Now, so that's considered as lifting one leg. Now, careful with this statement here. I said often one leg is enough. If you have just a freestanding device, battery operated meter, lifting one leg is fine. But if you have a meter that is kind of like complicated laboratory equipment, and it involves connecting that to power, you don't know whether this whole thing is separated from the rest of the grounding or power supply. You might have an active device that is connected to the ground somewhere else through the meter. And if this here is connected to the ground, right? And if you have another part of the circuitry, whatever it is, and if you have an active meter, which basically you plug into the wall, it could be connected through to the ground through some other circuitry internally, then it can cause some problems. So then you might have to remove the whole thing out of the circuit in order to properly measure that, all right? But that's what I meant by lifting one leg. Sometimes if you just have one free floating battery operated equipment, it's enough to just lift one leg. You don't have to remove the whole part, all the whole resistor. Okay, so that's as far as measuring the resistance. All right, my mouse, I apologize for my mouse. Voltage, resistance, measuring continuity, testing for continuity. Well, the continuity is true for a segment of wire if the wire is in one solid piece between the two measured points. You know what? I'm just going to let you read this slide here because I think I already talked enough in the previous slides about the continuity. I think I got some slides mixed up here, but that's okay. So measuring the resistance, you have to make sure that you remove the component. And I said one leg is just, lifting one leg is just enough. So that's measuring resistance of a resistor. You got to make sure one thing is that when you measure the resistance, sometimes you're going to hold the whole resistor and the leads, and just remember your body has certain amount of resistance between your two hands. So there's a possibility that you're going to put yourself in parallel with the resistor. So you might not get a true reading. So you gotta make sure that what touches the leads of the component is just the probes, not your body. All right. Testing for continuity. One example would be testing for a fuse. Right? The fuse should present a dead short between these two leads. If you switch the meter for continuity tester, you touch these two, it's going to give you the 0 ohms resistance, and it's going to go beep. It's going to give you the sound, right? Now, measuring current as opposed to measuring the resistance, sorry, as opposed to measuring the voltage. Here we have what the current is. Current amps is the flow of electrical charge through a component or a conductor. Current is measured in amps or amperes. Before measuring current with your meter, first you gotta disconnect the power source. Now we're gonna place the multimeter in series with that circuit that you're measuring in order to test for the current path. The full amount of measured current must flow through that meter. If you attempt to measure current in parallel with the circuit, you will blow the fuse inside your meter. And we'll analyze that a little bit in this couple slides. Select the highest current setting range and work your way down for most accurate reading. Yeah, because if you select If you don't know what the current is, if you select some lower range, like let's say there's 5 amps flowing and you select the 200 milliamps range, you're going to blow the fuse of your meter. Then reconnect the source and turn it on to perform the measurement. Well, here is the visual of that. Again, current pathway without the meter and current pathway with the meter. Notice the amp meter is in series with the whole circuit. So the whole current passes through the amp meter and through the rest of the circuit in order to take the proper measurement. Which brings me to the question of the internal resistance. The idea, again, of taking a measurement is to take the measurement but not affect the rest of the circuit or not affect the circuit's operation. Normally, what we have here is a piece of wire which has a 0 resistance, ideally. So in order to not affect the circuit, that device that is put in here after we break the wire has to have the characteristics that are as close as possible to a dead short wire. So when we were talking about the voltmeter, we're putting in parallel with the measured load. In order to not affect the operation of the circuit, it would have to have the resistance that's close to the air that surrounds it, which would be high, to not affect the circuit. But when we're using the amp meter, the internal resistance of this device should be as close to 0 ohms in order to, you got it, not affect the circuit. Because if the, well, let's say if this resistor R1 is 100 ohms, this resistor R2 is 50 ohms, we're going to have 150 ohms total resistance between these two. And if the amp meter has resistance of 50 ohms, then the total resistance changes to 200 ohms. So it will have a different circuit altogether. If the resistance is 0, then it's just like having a wire and the circuit is not affected. In reality, this amp meter will have certain amount of tiny itsy-bitsy resistance in order to trigger the measuring equipment that's inside. So it is going to be just maybe as, if you put in like 200 feet or 500 feet of wire instead of the one short wire. But the resistance of this device should be really, really small, as close to 0 ideally, in order to take the measurement but not affect the rest of the circuit. Measuring current, because the internal resistance of an amp meter is close to 0, you cannot stick the leads straight into the power source, because you're going to just, it's like sticking a wire between the power source. You're going to have something to limit the current. In this case, it's a light bulb. The light bulb has certain resistance. It's going to limit the current. And then you put the whole multimeter in series with the whole circuit in order to measure the current that flows through the light bulb. So how is it? The current leaves the positive side, goes through the load, goes to the positive side of the battery, goes through the battery, goes back to ore, leaves the positive side of the battery, goes through the light bulb, goes through that meter and comes back to the battery. Notice the polarity of the multimeter is important, because if you connect it in the reverse, the digital meter is going to show you a little minus that you have reversed the polarity. If you have an analog meter, so the analog meter is going to deflect deflect certain way. Here, yeah, it's going to deflect certain way in order to accommodate the scale. If you connect it in reverse, it's going to try to deflect the needle backwards, and there's no more scale there. It can actually damage the, well, the galvanometer that is inside the element. It can damage the element, right? Plus, before that happens, if you connect directly to the power source, you're going to present a zero resistance across the terminals, and things can go south pretty quickly. Okay? And here's the review. A meter capable of testing voltage is so you know what? I'm going to let you read this here, which is basically all that I said. That's the last page of the presentation here. Now, it's not the last page. It's the last page of the thing that we talked about. Different types of meters. A clamp-on meter. We're almost done here, guys. A clamp-on meter provides the ability to measure current without having to break into the circuit to do that. Can also be used as a full multimeter with additional probes. So here is the clamp, and we are passing a conductor through the clamp. You press on that here, and that thing opens, and you can clamp onto the wire. Okay. What happens in a conductor? When the electricity flows through a conductor, there's a magnetic field present around that conductor. This clamp has coils or inductors inside that are going to sense the strength of the magnetic field that is surrounding the conductor while the current passes through it. And based on the strength of that field, it is going to do its magic to calculate the current, is going to display the current value. So that's a very popular piece of equipment. Some are more expensive than others, and there's a reason for it. Other testing devices, a circuit tester, electrician's best friend. You plug that in, and based on the lights, it can show you that the circuit is wired properly or it is wired wrongly, right? Or it's not wired at all. Other circuit device testing devices. Here's the non-contact voltage tester. You can buy that in any hardware store. It's pretty neat, actually. If you have, see, there's a hot terminal of the duplex receptacle. You put that probe right to it, it's going to light up. And if you put it into the neutral, it should not light up. It is so nice and precise that if you have a cable consisting of two conductors, if you put that probe on one side of the cable, it's going to light up. You put the probe on the other side, it's not going to light up. So that's a pretty handy tool. It's a non-contact. It works on proximity. Doesn't cost that much money, but sometimes, and I'm not kidding you, sometimes it might save your life. Before you touch things, it's going to let you know, oh, there's a voltage there. Right now, that's as far as digital multimeters. One more thing I'm going to include that in the video description, famous last words. It is going to be this video right here. And it says reading voltages on analog display. And I use that analog spelling in different ways. Sometimes I spell it like this, or sometimes I spell it as analog. Both ways are correct, and I just can't seem to decide which ones to choose. So if you click on that, this is a 16-minute video. It is going to show you how do we actually use, what method we can use in order to read the analog display. And it is going to be on the test. You can bet on that. All right. I want you to know how to read analog display as well. And if you still have some, If you still have some questions, please don't hesitate. I want you to ask questions if you don't understand something. And the question is, will this be presented today? Yes, as soon as I'm done. It usually takes about 15-20 minutes to post the video on our YouTube playlist. Okay. Cool. So that's pretty much it. Look, it's an hour, full hour. You have all 2 minutes to get to the next class. All right, guys, have a great weekend and look for that video there on our YouTube playlist. And I'll see you when I see you next time I see you. All right. Thank you, guys.